Albert Einstein's general relativity laws allow for the existence of wormholes. In 1930, Einstein and his colleague Nathan Rosen calculated the mathematics of one of these intergalactic pipelines. It became known as the Einstein-Rosen bridge.
A wormhole is a solution of Einstein's equations for general relativity, telling us how gravity works. They're hypothetical, and what they do is they connect different parts of space and time.
The Einstein-Rosen mathematical wormhole arose from studying black holes. A black hole is a region in space of extremely strong gravity. The gravity is so strong that there is no way for objects that get too near to break away from its gravitational pull. Nothing can escape a close encounter with a black hole, not even light.
This inverted fountain serves as a visual analogy to what's going on around a black hole. At the bottom is the area inside the event horizon. And the water falling into it is analogous to gas that might fall into a black hole. Imagine yourself being a fish swimming around this region. Once you get down inside this central portion, you're past the point of no return.
But Einstein never intended his wormhole as a tool for space travel. His wormhole is theoretically created at some moment of time. It opens up briefly, then pinches off. Anything that tries to pass through it will get crushed when it squeezes apart.
The typical wormhole that you write down in your equations and study is unstable. It'll vanish in an incredibly short time. So what you need is some means of holding it open.
Scientists began to investigate whether there might be a type of wormhole different from Einstein's that is traversable. But traversable wormholes needed something to prevent them from pinching off.
You want to stabilize the wormhole. You don't want the wormhole to collapse. Keep the wormhole open. That requires something new called negative matter or exotic matter. We've never seen negative matter before. It would have anti-gravitational properties. But one day, if we ever find negative matter, perhaps that's the key to stabilize the wormhole.
The idea of a traversable wormhole captivated science fiction enthusiasts. It also reinvigorated the serious study of wormholes within the science community.
This transversable wormhole created quite a sensation, because perhaps it is physically possible to one day build a subway system to another galaxy.
Scientific ideas considered far-fetched today could one day become as acceptable as the fact that the Earth is round. The laws of physics may allow for the existence of wormholes, tunnels providing shortcuts through space as well as time. So could these cosmic subway systems theoretically be engineered into time machines? Einstein's general relativity laws reveal that time travel into the future is possible. They show that time is perceived differently depending on where one is in the universe and how one moves. Objects moving at close to the speed of light age slower than static objects. And objects near a gravitating body age more slowly than objects farther away.
Clocks run at different rates in different gravitational fields. The stronger the gravitational field, the more slowly time passes relative to someone out in space where there's no gravitational field. On Earth here, on the surface, our clocks run slightly more slowly than clocks high up in the sky. So an example of this is that the clocks in the GPS system of satellites run a little bit more quickly than the clocks here on Earth because they're in a weaker gravitational field. And the scientists and engineers developing the GPS system had to take into account the different rate at which clocks run. If they hadn't done that correctly, then your GPS system wouldn't work. If you were taking a trip from Los Angeles to New York, you'd end up somewhere in Massachusetts.
Forward time travel has been tested using highly precise atomic clocks. Scientists have placed one clock on the ground and another in a rocket flying high above the Earth. The two were compared using radio signals between rocket and ground. The clock on the rocket ticked faster.
Here on Earth, my clock is running more slowly compared to someone in a rocket ship somewhere further away from Earth. So their clock is moving more quickly, they're going to the future faster.
Physicists have studied whether wormholes could provide travel not only to the future, but also to the past. If there was a wormhole with one mouth near Earth and the other in the center of our galaxy, the rate of flow of time will be different at the one mouth than at the other when compared through the external universe. But when looking directly through the wormhole, the rate of flow of time appears to be the same. This difference in their relative ticking rates, as viewed externally versus viewed through the wormhole, would convert the wormhole into a time machine.